Today I'm going to be talking about theorems. This is intended to be an in-class lesson, so sorry if you're getting this for the first time from video. But theorems in calculus vary a little bit from theories, because theorems are something that's proven, it's backed up, we know it's true, as opposed to a theory is just something that we have a lot of evidence, but we haven't necessarily established that it's always true and forever true. Theorems are always and forever true, which is nice. Okay. Now, the first one we're going to talk about is one we've already gone over, the intermediate value theorem, and then the rest of them are going to be new. Okay, but let's go look at our nearpod today, which I'm going to be flipping back and forth, so it might be a little bit jarring, but sorry. Okay, so we're going to talk about this situation. I want you to imagine me driving from lunch back to work. So I've gone out for lunch during the day, and then I'm driving back to work. So at 12:01, you can see this is the speedometer of my car. At 12:01, you can see I was going 0 miles per hour. And at 12:09, about 8 minutes later, I was going about 61, 62 miles per hour. Okay, so this is the situation we're considering. So questions, like I said, this is meant to be in person, but we're just going to talk about them now. So did I go 25 miles per hour? Well, if at 12:01 I was 0 miles per hour and at 12:09 I was at 62 miles per hour, yeah, I would have had to at some point gone from 0 to 62, so I had to go 25. Okay, I can't just automatically turn my car on and I'm going 65 miles per hour. That'd be really cool, but not going to be a thing. Did I go 68 miles per hour? How did you know? Okay, so could I at some point in that 0 to 62 gone 68? Yeah, that's likely. I could have gone up, above 62 for a little bit, and I've just settled down to 62 at 12:09. But do I know for a fact that I went 68? I probably can't prove it. Like if I just gave you these two informations, like did I go 68? You probably wouldn't bet anything on it. Like I don't know, maybe, but probably not. Did I have to go 40 miles per hour? Yes. Okay. Same thing as the 25 miles per hour. 40 is in between that 0 and 62. So I had to go 40 miles per hour. Did I go in reverse? Well, reverse would be, it wouldn't really show it. But reverse would be like negative speed. Once again, could have gone reverse, but that's kind of less than 0. So I can't prove that I went in reverse. Did I go 70 miles per hour? Same idea as your 68. Outside that range of 0 to 62, so I could have, but there's not really a way to prove it. So the big thing that we want to be jumping on is anything between 0 and 60, because my car, the big thing is that my car is not stopping and, maybe I'm braking, but I'm not turning my car off and getting out and then jumping back in. I went from 0 to 60 of continuous car being on. Okay, keyword is continuous this whole time. So what speeds are guaranteed and how would we know this? And I'm going to draw a little graph real quick, and we're just going to, be easy with the numbers and such. So we'll say this is 0. And we'll say this is 6 or 9 for our time. And then this is 0, and we'll say this is 60 up here for our speed. So I was at 0, 0, at time 0. And at time 9, I was just a little bit above 60, so about 62. Okay, so I just want to draw a graph. So could I have gone like this, really accelerated, then kind of gone up, maybe gone a little bit up, and then kind of continued on that speed the whole time? Yeah, that one works. Could I have done this, leveled, then maybe sped up a little bit more, then kind of leveled, and then kind of looked that? Yeah, that graph is true. Okay, could I have gone, maybe started, going real slow, then maybe braked, then started back up, then sped up a bunch because I got on the highway, and now I'm going 62. Okay. All of those work, yes? Okay, the key thing is for all of these, all of those values in between 0 and 60 are guaranteed. Okay, at some point I could have gotten faster than 60. At some point I could have gotten less than 0. I could have gotten reverse. Okay, probably not, but I mean, could have. But all of those values in between 0 and 60 on the interval 0 to 9, 12 o'clock to 12:09, all of those values are guaranteed. Okay. This is what leads us to our conclusions on the intermediate value theorem. Let f be a defined continuous function on a to b, and let s be some number in between the y values f of a and f of b, the y values at the endpoints. Then there exists at least one value x on the interval a to b such that f of x is equal to that y value s. So as you can see in that picture, if f of a is down here and f of b is up here, and s is somewhere in between a and b, it has to happen on that interval as long as it's a continuous function. Okay, so let's go back to our notes. Okay, IVT, intermediate value theorem. So what must be true? Okay, things that must be true is that f of x is continuous on the closed interval a to b. So it's a continuous function. We can't have any weird breaks. Okay. The second thing that must be true is that k is in between f of a and f of b. Okay. So that value k, that y value k, is somewhere in between f of a and f of b. The conclusion that we reach is that there exists, and this is the symbol for there exists, okay, trust me, I was a math major in college, there exists a c on the closed interval a to b such that, okay, that's the abbreviation for such that, f of c is equal to k. Okay, so what that's saying is, just like we said before, is that somewhere on that interval a to b, I have to be equal to that y value, because the y value is in between the y values at my endpoints. So if this is my c right here, then boom, 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 right here would be our point where f of c would be equal to k. And notice how it is in between f of a and f of b. Okay, so that's IVT. That should be familiar. Okay, now before we jump back to the Nearpod, limit definition of a derivative. We have the limit as h approaches 0 of f of x plus h minus f of x over h. So limit definition, it's used to find the derivative, so it is equal to f prime of x. And these notes, y'all, are just kind of a short, something you can refer back to kind of know all this information. The second one, the limit as x approaches c of f of x minus f of c over x minus c. This is actually called the alternate limit definition of a derivative. You've probably seen it in a multiple choice question or so that I've put out there for you. It essentially means the same thing as the limit definition of a derivative. It's used to find the derivative, but it's used specifically to find the derivative at the point c. Okay, so that's just the only difference. It's another way to find the derivative. We can also use LDD to find the derivative at a point c if we just plug in for a value of x. So it's almost kind of redundant as a function, but you'll see it sometimes on the AP exam, so it's just good to know. Okay, next theorem we're going to talk about is the extreme value theorem. So let's pop back over to our Nearpod, and we're going to keep on keeping on. Okay. On the graph below, we're going to plot a continuous graph on the interval 3 to 19. Okay, not too crazy. Ooh, not text. Go away. So this is 3, and 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. 19. Okay, and we're going to plot a continuous graph. Okay, we'll do this one to this one. Okay, continuous, so swoopy. All right, that's easy. Okay, let's do another one. What about, I could just do a nice straight line. That's continuous. Okay, what about, go down and up and then kind of do this and I'll mess around and boom. Okay, that one's fine. It got a little wonky at the end, but still fine. I could even do something really crazy. We could go up and then down and then level and then up and then down even further and end here. Okay. So all of these graphs are continuous functions from 319. There's no breaks, there's no holes. The limit exists everywhere. All the points are defined. We're continuous. Okay. What I want you to notice is that on all of these continuous graphs, at some point on this continuous line, the graph has either a maximum value, so it has a value that's the highest on the interval, or a minimum value, a value that's the lowest on the interval. So like for our yellow graph, we have our max up here, and we have our min. Okay, for our blue graph, let's see, this one looks a little bit lower as our min. And then our max, the highest we ever came to, was the same spot as these endpoints. Okay, but it doesn't really matter because your max can occur in multiple spots. The maximum refers to the y value. Where it occurs is just the x value. Okay, on our green function, it looks like this would be our max up here. And our minimum looks to be about right here. And then on our red function, obviously I didn't draw it straight, but it was supposed to be a straight line. So,
at this time, please.
So even though it's the same value everywhere, that same value is just both the max and the min. So it still has a maximum and a minimum. Well, this is the extreme value theorem. Okay, the extreme value theorem, if f is continuous on a closed interval a to b, then f attains an absolute maximum value f of c and an absolute minimum value f of d at some numbers c and d in the interval a to b. So a couple little examples down there, but all of those functions, no matter what they look like, if they are continuous, have a maximum and a minimum. Okay, so let's go and add back to our extreme value theorem on the previous page. So what was the only thing that had to be true for the extreme value theorem? The only thing that had to be true was that the function was continuous. So f of x is continuous on that closed interval a to b. Notice that some of our must-be's are starting to line up. Conclusion, if it was continuous, then f of x has a max and a min. Okay, so if this is our nice little continuous function here at f of a, that would be our min. Here at f of c, this would be our max. Nothing too crazy. Extreme value theorem is the easiest one. It's the one that needs the fewest conditions. It's just if it's continuous, then it has a max and it has a min. Let's talk about the mean value theorem. So the mean value theorem, heading back to our Nearpod. Given continuous function f of x is equal to x cubed, what is the slope between points 1, 1 and 4, 64? If possible, find a point in the interval 1, 4 that has the same slope as your answer above. What is the slope at a single point called? Okay, so I'm going to go over here to this next slide, which is a Desmos. Okay, and we are going to graph our function just as they wanted us to. So f of x is equal to x to the third. And then over here, we're going to graph those 2 points, 1, 1. And we'll label that so we can see it. And our second point, 4, 64. And we'll label that. And then let's adjust our set just a little bit. So x is going to go from 0 to, let's do 6. Maybe we'll go a little further, -1. And then our y-axis, we got to go all the way from 0 to 64. So -1 to 70. All right. So hopefully we can see this graph. Okay. So as you can see on the graph, we have a point here at 1, 1. We have a point here at 4, 64. And what we want to find is we want to find a point on the graph where the rate of change between 1 and 1, 1 and 4, 64 is the same as the rate of change at that specific point. So real quick, we can find that rate of change, f of b minus f of a over b minus a. That's our average rate of change. So 64 minus 1 over 4 minus 1. Okay, that'd be the value 21. So I'm just going to, then let's see. And then we're going to take our derivative, because remember, I want to find a point where the slope at a specific point is the same as the slope between the 2 points. So my slope between the 2 points is 21. My derivative would be 3x squared of x cubed. So 3x squared. And I'm going to set that equal to 21, which would give me a specific point y where the slope in our graph would be 21, 2.646, 18.52. Okay, and you're probably like, Mr. Arbone, this is so much math. What's happening? Just bear with me. You're about to, the epiphany moment is going to come, right? So I'm going to put a tangent line through our point 1, 1 and 64 or 4, 64. So our slope would be 21. We can use point slope form with either of our points. So y minus 1 is equal to 21 x minus 1. Okay, so notice how we have that nice straight tangent line going there through the points 1, 1 and 4, 64. And then I'm going to make another tangent line equation, but this time right here at the point where we intersect 2.646 and 18.52, but with that same slope. So y minus 18.52 equals 21 parentheses x minus, this is a little hard to remember, 2.646. 2.646. Look at that. So now at 2 different points, I'm going to cut this out so we can see it. So at 2 different points on this curve, or basically at 1 specific point on the curve, sorry, we have a tangent line to this curve, okay, that has a slope of 21, which is identical to the average rate of change, our slope of 21 on the entire curve. So we found a point between 1, 1 and 4, 64, where the slope at a point was the same as the slope over the interval. So our tangent was equal to our secant. Our average rate of change was equal to our instantaneous rate of change. Now, that some things that have to be true, okay, well, for one, this is a continuous function along that interval. Yes, 1, 2, 4, okay. Second, this is a function that I can take the derivative of. If I'm comparing the derivative to the average rate of change, I have to be able to take that derivative, okay? So those are the 2 things that have to be true for the mean value theorem. The mean value theorem, the condition is that it's continuous on the closed interval a to b, differentiable on the open interval a to b, and if those 2 things are true, then f prime of c, the tangent or the derivative, is equal to f of b minus f of a over b minus a, the secant line. And we can see that in this example here as well, just like the example that we did, that the tangent line would be the same as the secant line somewhere on the curve. Or, in layman's terms, a rock equals I rock, which is what we've been doing this year. So let's go back to our theorems real quick, and let's add in that information. So if f of x is continuous on the closed interval a to b, and f of x is differentiable on the open interval a to b, then our conclusion is that there exists a point C such that f prime at C is equal to f of B minus f of A over B minus A. Or, as we said, A rock equals I rock. Okay, or I wrote that backwards to what I wrote up here, but I rock equals A rock. Same difference. Okay, so over here on our curve, as we can see, we have A to B, our continuous function that's also differentiable. Our average rate of change on the curve is that line there through the middle, that secant line. And we actually have multiple spots here. So we could have multiple spots where the mean value theorem is true. There exists a point C, really just means, I guess, at least one is really what it should say. So at least one point where the instantaneous rate of change is equal to the average rate of change. Okay, the very last one we're going to talk about is Rolle's theorem. I know it's the only one that doesn't have mean value, extreme value, intermediate value. It's a little different. It was invented by a guy named Rolle's. He's pretty cool. So let's go back to our Nearpod real quick. And here on Nearpod, we're going to let 2, 1 and 6, 1 be points on a continuous and differentiable function f. We want to sketch possible graphs of f on the closed interval 2, 6. Okay, so 2, 1 would be like right here. Sometimes it just doesn't like me writing. There we go. And 6, 1, 3, 4, 5, 6. I realize in retrospect, this is not the greatest graph in the world. Okay, so the big thing that I want you to notice, okay, is no matter how I go from these 2 points, so let's say go swoop, okay, so I could do that. I could go down low, like that. I could go straight across. I could do all sorts of wonky things, okay? No matter what happens on my graph, what you should notice is I always form, if I'm starting and ending at the same y value, I always form these points where the curve has to rebound on itself. Even if my line is perfectly straight, that point is just everywhere, right? Okay, so I'm always forming these points where the graph has a, specifically for calculus terms, a horizontal tangent line, which is important, okay? So if I'm always forming these points where the graph has a horizontal tangent line, and bear with me, Nearpod's gotten a little slow as the evening has gone on, okay? Now let's change it up a bit. If the points were instead 2, 1 and 6, 3, we're going to sketch 3 possible graphs. So 2, 1, still same spot. 6, 3 now though. 3, 4, 5, 6. 3. Okay. So if instead I am not at the same y value, well, I could still go up like that. I could still go down like that. I could also just go straight there, kind of linearly, right? Well, now with my going up, I have tangent line. With my going down, I have that horizontal tangent line. But with my middle graph, my just linear relationship, I never have a spot where I rebound, okay? So because I'm not starting and ending at the same y value, I don't necessarily guarantee that horizontal tangent line. So this is the important result that we found with Rolle's theorem, is that if the function is continuous, the function is differentiable, and the starting y value and the ending y value are the same, then no matter what, somewhere on that interval, I have to have a point where the derivative is equal to 0. Okay, so all these different examples you can see, I always get at least one point if the starting and ending y value are the same, where my horizontal tangent line occurs, where I have that derivative is equal to 0. So let's add those last conditions here. to Rolle's theorem. So must be true. F of x is continuous on the closed interval a to b. F of x is differentiable on the open interval a to b. And f of a is equal to f of b. So if all these things are true, then there exists a C, not an f of c, a C on the closed interval a to b, such that f prime of c is equal to 0. So say right here, this is my C, then this would be f prime of c equaling 0, that point where we have that horizontal tangent. Okay, y'all, this concludes our video notes about theorems. Sorry if it was a little bit wonky. Like I said, this is supposed to be an in-class notes, but if you didn't get this in-class portion, this is a nice little supplement of me going through the Nearpod. Please, please, please watch it if you need it. Otherwise, I will see y'all in class.